maybe we'll let them finish their food and walk in. But thank you all for being here. It's obviously the weather kind of took a turn for the worse, but it could be a lot worse. It could be almost anywhere else in the United States. But thanks for braving the elements and coming out. So this is our first talk of the spring semester. We're still in a little bit of flux of the second talk because of the government shutdown. As you may have, if you've been following the website and stuff, we had the February 21st date, then we moved it to the 28th. We've tried to talk to them about the 7th, but that's exam time here, so we're trying to do March 6th. And that, we're still waiting for confirmation from Nikki's office. So that will be a talk on the Parker Solar Probe, which if you follow this stuff is the spacecraft that we sent into the atmosphere of the sun. It made its first perihelion in December, and it's got another, I think, 24 to make over the next couple of years. And so the chief scientist, Nikki Fox, is going to be coming to talk about that. April 4th, we're going to have George Abbey. Some of you know George, former director of the Johnson Space Center. A new book is out called The Astronaut Maker, which is a biography of George Abbey. And since we're building up to the 50th anniversary of the moon landing, that's a kind of one of the things that we're trying to do is get, and so George will be in here. We also have a space day at the baseball game on Ryan, help me, April 13th, April 6th. There'll be, I don't know who we're playing, but some kind of American sport called baseball. And I'm sure Rice will win, but we'll also have a space day during that, so we're working that. Well, baseball, football, you know. Anyway, so again, baseball, thanks for being here. Well, again, if you get the mailings, you'll get all information about these events. If you look on the website, you'll see them, and there'll be a few other little things here and there, I think, that are happening, that is happening. So our tonight's speaker is someone I've heard about for the last several years. And now that we have some students who are really interested in the whole CubeSat issue, within quite a wide radius, of several hundred miles, maybe even 1,000 miles, the expert in all of this is standing on the stage, and it's not me. So I was really excited to be fair to Helen, she did this at quite short notice because I'm very badly organized. And so early January I said, hey. And she kindly agreed to this, so I'm really excited about that. So let me introduce Helen a little bit to you. Usually I go through their bios and cut some stuff out to keep it short. It's really hard to do this with Helen because she's got quite a record here. So currently Dr. Helen Reid holds the titles of Regents Professor, Presidential Professor for Teaching Excellence, and is the holder of the Edward Pete Aldridge 1960 Professorship within the Department of Aerospace Engineering at Texas A&M. She founded and directs the AggiSat program, which is a small satellite lab that involves a lot of students, and I think that's what we're going to hear a lot about tonight. Small sats and CubeSats and so on are all the rage currently. And she also is in the Computational Stability and Transition Laboratory. And I presume it's not the laboratory that's in transition or unstable. She's a co-founder and chief technology officer and member of the board of directors for Chanda Space Technologies. Adil Jaffrey is a good friend of Rice here, and that's his company. 26 years of experience in micro and nano satellite design and operations. She's a fellow of the American Institute of Aeronautics and Astronautics, the American Physical Society, the American Society of Mechanical Engineers, and she was selected for the 2018 AIAA National Academy of Engineering third Yvonne C. Brill Lectureship in Aerospace Engineering, the 2018 AIAA Fluid Dynamics Award, the 2016 ASME Kate Gleason Award, the 2007 AIAA American Society of Engineering Education J. Leland Lee Atwood Award. They need to shorten these titles, and the 2014 Minnie Stevens Piper Professor Award. So obviously a very talented, well-respected professor in a very important topic. Please join me in welcoming Dr. Helen Reid. Thank you.
Thank you. Howdy. Good. All right. Thank you so much for having me. It's really quite a pleasure to be here, and I enjoyed talking with some of you already. Look forward to talking with more of you as we go on. Is the mic amping okay? All right. Just let me know. So tonight I'm going to talk about the topic of expanding space and creating the next generation of space explorers in the process. So I'm going to talk about small satellites from a personal viewpoint. So I'm going to introduce my experiences in working with small satellites, and has been pointed out, it's been principally through working in the university environment. And then I will talk about why working with small satellites in a university environment is important, why are small satellites important to the profession, and so forth, which will lead into then the impact that small satellites are having on the profession. I'll talk about the challenges and the opportunities with the high interest in small satellites. I'll talk about then my current activities, the things that I'm working on at A&M, and then I'll leave you with some takeaway messages, and I'll take questions then after that. So I actually got started, now close your eyes. Okay, all right. So I actually got started in small sats back in 1993, and I was at Arizona State University before coming to Texas A&M. And my background had been in aeronautics, in energy efficient aircraft, thus the other lab, the Stability and Transition Lab. So I was made director of the Aerospace Research Center in the College of Engineering back at Arizona State. And my job was to get local industry involved with the students at the university. And of course, the Phoenix metropolitan area, I mean, you could build a whole space system, you know, from orbital sciences with the rocket to all the different satellite parts. We had Spectrum Astro, we had Honeywell, we had Motorola, we had everybody in the Phoenix area. So first thing that happened, or the thing that happened that got me started into small sats was one day a young man came and knocked on my door, and his name was Joel Rodemaker, and he had just come from CU Boulder, and he came in and said, I worked on a small satellite at CU Boulder. Could we start a small satellite program here? It sounded reasonable, so I said yes, and then we put it together from there. So we went around to the various companies in the area and met with Scott Webster, who was one of the co-founders of Orbital Sciences, and he thought that was a good idea to start a satellite program up at Arizona State in the neighborhood. So he offered us a free ride, a free launch, if the students could build a 10-pound satellite. Now, in 1993, that was a very, very aggressive goal. Now it's kind of, you know, every day you hear about small sats and things like that. But at the time, that was a very, very visionary proposition. And we decided to go with it and built the program from there. We went to Honeywell, told them we had this free ride and a 10-pound satellite, and the first thing they did was laugh at us. You can't put anything in 10 pounds and have it work in space. But they were intrigued. The students really wanted to do it, and they actually became some of our biggest supporters. And so I credit them with really helping us, you know, get the program up and going. So I left Arizona State in 2004 and came to Texas A&M. So the lab back at Arizona State we called ASU SAT Lab. And we had two major missions that we were working with. This ASU SAT-1 was this mission that had been proposed by Orbital Sciences, by Scott Webster. And so we ended up, after some years and putting it all together, we ended up launching on the first Minotaur, which was called JAWSAT. And this was in January of 2000. We worked, it was an Air Force launch, so credit Major Buckley with helping the students actually realize their dream of putting a satellite up in space. So you see the ASU SAT-1 appended, here it's in its ESD bag. It's appended to, it's right here, it's appended to the JAWSAT structure, which is on top of the Minotaur rocket. Here's the rocket launching. But you see it was a size, just a structure that fit in your hands, and that was one of my graduate students holding it. The students actually decided to do some different kinds of technologies. I kind of let them figure out what they wanted to do with it. They decided to make an all-composite structure, so they laid it out and everything. So there was an aircraft parts company down at the airport at Phoenix Sky Harbor, and they wanted to kind of get into the space business. So they offered the students use of their autoclave to lay out this little structure. Of course, this autoclave was immense, and our little satellite sitting in the middle of it was kind of interesting. But they helped us out with curing the satellite, and it was successful, and now they could say that they were in the space business. So establishing these partnerships with companies as you're setting up a student program has been very, very rewarding, and I thank each and every one that worked with them. So then the next mission that we did, in around the 2000 timeframe, 1999, the University Nanosat program got kicked off with the Air Force. And so we applied for that. We teamed up with CU Boulder and New Mexico State University, and Arizona State was the lead. I was the lead PI. And so we were actually the first winners of the University Nanosat program. So down here you see our 3 satellites that we built as part of the University Nanosat program. So originally, each one of these is 18 kilograms in mass. And originally we were supposed to go on the shuttle, but then the Columbia accident happened. So they had to remanifest the satellites. So they couldn't send them in this configuration, but they sent them more in this configuration, 2 split off. So instead of flying 3, we were able to fly 2, but on the Delta IV Heavy rocket. And we were appended to the side of this chunk of aluminum, instrumented chunk of aluminum, to demonstrate the geotransfer capability of this large rocket. And so you see us appended onto here. And this was one of my students working on the satellite before it was attached to the side of the rocket. So then, in addition to those, to the 2 missions there, we also teamed up with Jet Propulsion Lab. We had a relationship going, and we worked with Robert Shotwell at NASA JPL. And at that time, I was also running the space grant program at Arizona State University. And so what we wanted to do here was, the idea was to plan a mission to Mars. We really wanted to send this mission to Mars back in this time frame. But then NASA changed its priority from going to Mars to going and doing things on the moon. So the project kind of got put on the back burner and so forth. However, the students made really good progress with it. The mission was called MIMIC, and we were measuring the magnetic field on Mars with various instruments with this concept. So you see my 2 students here. You see Senator McCain in the picture, Sean O'Keefe, former NASA administrator, and other dignitaries in there, related to this mission that we were going to do with the Johnson Space Center, Jet Propulsion Lab. The space grant, when we brought that in, we were going to try to bring in every space grant in the union that wanted to work on this, to try to have a collection of different space grant programs, have their students work on this collectively, and send the mission to Mars. So then down below here, you see a bunch of other projects. What I have found over the years is if you're establishing a satellite program, it's also good to have even smaller projects. As you'll find as you're getting your CubeSat mission going, it will probably take a little longer than you think to go from the beginning to launch, okay? And we want students to leave. We want students to graduate and leave, so we don't want to keep you around until it actually happens. So it's good to have smaller projects that maybe you can fit into a semester or 2 semesters, and then the students can see a project from cradle to grave, and they get the whole experience. So I actually did this great moon buggy race, which was basically a competition at the NASA Marshall at the Space and Rocket Center. And so the students had challenges to build basically a human-powered moon buggy, basically bicycle parts, and had to fit initially in a 4-foot by 4-foot by 4-foot cube. They had to assemble it and then race it around a track around the Space and Rocket Center. So that was a lot of fun, and I did that for 10 years. And we were the Moon Devils. The Arizona State was the Sun Devils, so we decided to be the Moon Devils on that one. So we took some best designs, but I think our favorite award from that was Best Crash and Burn. So it was really a lot of fun, and again, it's there for team building. It's for encapsulating smaller projects where students can actually see the beginning, the writing the proposal, making a concept, all the way to finishing and then reporting out the results. So these were all very valuable. We also, there was another project out there, and I had some journalism majors come in, and they thought that looked interesting to them. It was called NASA Means Business. And so what the object was NASA wanted the students to make public service announcements about going to Mars. Well, these students really, the journalism students really hadn't studied, the NASA program and things like that. But it was a way for them to go in and actually learn about what NASA was doing and going to Mars. And so then they got all excited about it. And they created a PSA, and they took first place, the grand prize. And so this was Arizona students proposing interesting research experiences. Okay. You got to be good with acronyms as part of this. So that was a lot of fun, and that got another set of students involved in what we were doing. So with these projects, I found it's very, very valuable to open them up to all majors on campus, anybody interested, because it takes everybody to do a space program. And this was a neat way to try to integrate other majors, maybe some non-traditional majors, in with what we were doing. SubSem was a sounding rocket program, so we did a sounding rocket out of NASA Wallops. The students actually put an instrument on there. Of course, we've done CanSats. Have you guys done CanSats, soda can size satellites that you put in the top of an amateur rocket and send them up and then they parachute back? That's also another very neat little project. And I've seen the CanSat competitions. I know SEDS is looking at this CubeSat competition, but there are also CanSat competitions out there as well. Again, basically the size of a soda can, okay? Send it up 100,000 feet or however high you're going, and then you can operate it, but it's a nice contained little project, maybe to learn some of the systems engineering and project management and things like that. Balloon sats, again, this is using weather balloons to send payloads up to altitude. I did several of those as part of the program. And then A0G, of course, that was the Vomit Comet that was flying microgravity experiments, and AZ for Arizona. You got to be clever in this. For a while, I managed the solar car team. We went to the Indianapolis Speedway. That was really cool. I got put in the rental car with the race car driver. Oh my God, I was so happy to get out of that car alive. And then micro UAVs, you can branch off and do other things if students want to do them. And then NASA has had, at least at the time, had programs that the high school students and elementary students could do, sending small payloads up on the space shuttle and getting them back. And so what I've really found to be really kind of fun about this is to find all these other opportunities, look for these other things, and if the students are interested in doing them, I mean, you guys are interested in doing them, go for it. They're a lot of fun, and they really bring you some experiences. Okay, so I moved to Texas A&M, just up the road, and so now we became AggieSat Lab, obviously. 2005, I set it up again, and it's still running today. So we've had two major missions. We got a relationship going with the NASA Johnson Space Center in a project called Lone Star. And so this was low Earth orbiting navigation experiment to study autonomous rendezvous and docking. Lone Star. Okay, so we had two missions. We were teamed up with the University of Texas and to build CubeSats. Okay, now you've heard this term CubeSats, and that was kind of advertised as part of this talk, this idea of CubeSat. So each one of us had a form factor to build a single CubeSat. These were 5-inch CubeSats. Now, if you've heard of CubeSats, you're probably thinking of the 4-inch. And I brought some props today just so you get a feel for what we're actually talking about as far as size. Satellites are traditionally very large, what you think of. This is a CubeSat. All right, this is a self-contained, talk to it, does experiments. This is what we're talking about. Well, this is what you're probably, if you've heard of a CubeSat, this is probably what you've heard is the 4-inch on a side. Well, this was the DoD standard. This was 5-inch on a side because the space shuttle had a launcher embedded in the bay, in the payload bay, that would launch these 5-inch on a side CubeSats, the Space Shuttle Payload Launcher, SSPL. So our first mission at Texas A&M involved creating these and then launching them. So that's what's going on up here. So this is actually, we built the CubeSats, the two schools, and that's actually a picture in space after it's been released from the space shuttle. And that was the most beautiful picture I'd ever seen. The atmosphere and everything was just incredible. So I thought I would bring the engineering model for that. So this is, it's traveled a lot. So this is the engineering model that we created. So this is pretty much exact replica of what we actually sent up. This is exact size, okay? So, so this is what we were talking about. And released from a launcher. I know some of you were talking about working with nanoracks, and so it's something that pushes the satellites away from the launch vehicle very, very quickly. We launched this thing at the end of July in 2009. We communicated with it within a few minutes, or at least a ground station around the world. Again, we had a network of amateur ground stations around the world helping us find it. And then we talked to it 4 hours before it actually burned up in the atmosphere. So we got the data that we needed. So NASA Johnson, the value of these, they were testing out a new GPS system in this. So it was called Dragon, for dual RF, et cetera, GPS system. So Dragon set. Okay. So so that was AggieSat 2. And then the next mission that we did in that series was called AggieSat 4. And people kid us, it looks like we've gone to do even numbers. Stay tuned, it gets better. So AggieSat 4 then was our next mission. Now this one we had a form factor of 50 kilograms to work with, and a 2 foot by 2 foot by about a foot tall structure. Okay? And the idea on this one, again, we were teamed up with the University of Texas again. They decided to do a 3U. So what we did on this one, and you see the structure in the lab, this is the actual satellite that was delivered to NASA. So we put one of these launchers inside of our bigger satellite, and we put the University of Texas 3U. So this is a 3U. It's 3 1Us put together. Okay? And this is a 3D printed model of a sample 3U. Okay? So this was actually inserted into the satellite, and then we sent it up into space. The neat thing about this, you see this foam box right here? This was not attached to the side of a rocket, but rather this was a new way of doing it. It was packed in foam, like luggage. So it was sent up on OA4, and then it was unpacked on the station by, and here, there's Scott Kelly unpacking our satellite here. We've actually signed it. All of our signatures are right here. So he unpacked it and put it together, put the antennas onto it and so forth, and then it was released out the Japanese airlock into space. And so you see our satellite then released into space. That was back in the 2015-2016 timeframe. So then after that, we've started some new projects. And so new projects we're looking at, the students decided they wanted to get into 3D printing. 3D printing is a really hot area because, if we're going to go to other worlds, or if we're going to do things in space, or go to the moon or something, you can't send home for parts and things. So it'd be good if you could print your own systems. So the students have decided this project called SAMS, for Space Assembled and Manufactured Satellite. They came up with a design that they could 3D print. Now there's a 3D printer on the International Space Station. So the students worked with NASA here and Made in Space, a company that does 3D printing. So we came up with a design. This is an older design. I just have this for demonstration purposes. So this is all 3D printed. So they sent the instructions up to the ISS, and we're in the queue to have this printed up there, okay? And then they're going to send it back down for us to inspect. The goal will be eventually we want to 3D print a whole CubeSat up there. We'll have to send up some extra parts to put it all together. We'd like to 3D print it up in space and then have them, release it off in orbit, and then we work with it. So this is very, very relevant to technologies that are going to be needed as I said, go off into other worlds and things like that. And you can't phone home to the hardware store for parts and things. So another project we worked with was a project called Stair. And that was with Lawrence Livermore in the Naval Postgraduate School. So on that particular project, we did the structural and thermal analysis. And this is the 3D printed model of that CubeSat. Okay, and you can see all the different parts, the different control mechanisms. There were telescope in here and so forth, all packed into this thing called 3U. So 4 inches on a side and 12 inches tall. So this is based on the Colony 2 bus, the National Reconnaissance Office bus from Boeing. And so we had 2 launches on that. We went up on an Atlas V in 2012, and then we went up on a Minotaur in 2013, flying these kinds of systems. So the students got good experience there as well. So in addition to these satellites, what we also do is we have a really good relationship with the Aerospace Corporation. So up on our campus, we actually host one of their ground stations, and this is one of the ground stations that they use to watch their CubeSats. Aerospace Corporation sends up a lot of CubeSats, AeroCubes, maybe some of you have heard of. And so our ground station helps them track those. So it's been a very, very good partnership. And again, at A&M, I did the balloon sats. We did an Air Force robotics competition. The students wanted to do that. This was basically building a robot in an office situation. It was supposed to be kind of a hostage situation. So you had to build a robot to go into a room and figure out who was the good guys, the bad guys, and report that out. So we had competition with the University of Texas, and then a couple of schools from down here in Houston. So our kids took first place. Texas was third. I want to mention that. Okay, and so the idea here was the students decided that they had to be stealthy, so they couldn't know something was coming in and monitoring them. So what they ended up doing was they made their robot as a box of computer paper. So they made the robot, and then they slipped over a box of computer paper. And the thing just slowly walked itself in the room, parked itself under the printer, and then just surveyed the whole room. And that was kind of fun. So that was kind of neat. NASA Johnson has competitions in the Neutral Buoyancy Lab. So the students decided they wanted to try that. So this was related to studying asteroids. So we did that one year. The students wanted to work with the Jet Propulsion Lab. We looked at e-sails, an e-sail, which is a way of moving around in space. And then I just recently was working with the Zero Robotics program with MIT, and that's a program for middle schoolers where they use these robotics that are on the International Space Station right now. So they let middle schoolers code the movement of the spheres that are on the International Space Station, and then they compete against teams from all over the country, and in fact a couple from around the world. So that was a neat program that I did last summer with middle schoolers. Okay, so that's kind of what I've been involved in. It's been diverse and it's been a lot of fun. So I've come to think that related to undergraduate education, my philosophy is that the ideal experience would consist of students taking the traditional classes because they are exceedingly important to get the basics, but to complement that with a 4-year participation, come in as freshmen and work on these multidisciplinary, extracurricular, hands-on student-run projects. I say extracurricular, the students are taking their regular classes and they're doing this in their free time to come in and work on these extra projects. We have been geared toward the design, build, fly of operational small satellites. I want these satellites to advance rapid and low-cost solutions and new technologies. I want the things that the students create to actually be important to feed into national initiatives in space utilization and exploration, and also possibly into national security needs. And while we're doing that, I want them to learn industry practices. I don't want this just to be throw it together, but we have a rigorous set of practices in place that the students learn about. And so we try to accomplish this all within the university environment. So since 1993, I've had way over 1,000 students, undergraduate students, that have participated on these projects. We've had some 55 different companies that have participated, have seen that this is kind of exciting. 7 NASA centers and 10 Air Force and other federal agencies have participated as mentors, as helping out the students with various aspects, as well as we've partnered with some 15 different universities in these programs. And each one of these partners has brought really something very valuable and very unique to the students' experience. And it's just been a fantastic experience. So I mentioned this already, but one of the key facets of this program that you really want to capitalize on, and I heard that the CubeSat program is doing that here, is to strive to be interdisciplinary. So not just engineering, but we've had business majors, science majors, liberal arts majors, communication majors. You heard about the journalism majors. We've had social work majors. We invite anybody on campus that has an interest in doing this to jump in and start working on the project. And then we've had industry and government affiliates on here. And you see We do want freshmen on the team. I want freshmen on there, and this actually helps with the with continuity. You'll find that with your satellite program, that if the seniors are just doing it and then they all graduate, there goes your corporate memory. So it's good to have younger people, or less experienced people, let me say, less experienced people come in to learn the ropes, and then they pick up the leadership positions as they go along, and they help sustain the program as it goes forward. As I said, any student on campus is welcome to join. The students are simultaneously pursuing bachelor's degrees, or even in some cases their graduate work, masters and PhDs. Okay, so why small satellites? Why is it important to have a small satellite program in a university? So why not something else, or what's the purpose? Well, students love spacecraft, they love rockets, they love airplanes, and I think all the students in here probably have some configuration that they really are passionate about. And so by having a real system, it attracts students to come in and want to work on it and learn these extra, gain these extra experiences. So it's a magnet. A small satellite is a magnet, especially one that's going to actually be launched, and they're going to have to operate, and they're going to have to work with NASA, or they're going to have to work with the Air Force. It's really quite the magnet. And the other part of this is the students have to design, build, and operate real aerospace systems under real government and industry constraints. This is not a homework problem where, okay, if you didn't quite get it done, you go and ask the teacher, can I have a delay, and things like this. If you don't make certain constraints, you don't fly. So it gives the rigor to the students in something that they really passionately want to do, and they do see that there are these constraints. They also not only have these kinds of constraints up here, but also strict resource constraints, as you will find, in size, weight, power, and so forth. Financial and regulatory. I mean, you can't put a whole lot in this, okay? You really have to think about what goes into this small system here. You don't have a lot of power, so you have to really optimize what you're doing and really think about what you're doing. Financial, we're in a university. We don't have the big budgets of a government lab or something like that. So we have to work under financial constraints. And of course, regulatory. Just because you're in the university, you still have to work with the FCC for licenses for communications. You have to work with NOAA if you're taking pictures. So you have to work in the regulatory environment as well, and that can affect your design process. So these constraints actually are positive because they encourage students to creatively think. Do they want to take on that extra constraint, that extra thing that they have to worry about to perform tasks, or can they do something more simply and work around that? So, and the other thing is the context for this program is in advancing small satellites, and students might say, well, I don't want to build small satellites in my career. Well, the point is, the things you're learning in a program like this skill set is actually applicable to a wide variety of disciplines and industries. So you're learning about how to do systems engineering and project management, be subsystem leads, and do testing and integration and all this stuff. And this actually applies to a wide variety of disciplines. So, so what's the impact of these things on the profession? Again, students are building these in the universities. So, so what? Well, the state of the profession, more traditionally, was if things were being monitored in space, traditionally done from the ground. Things were done from the ground, ground-based systems. And if things were flown in space, they were typically very large, high cost, long life, 15, 20 years or more, highly integrated and capable, basically Battlestar Galactica kinds of satellites, low risk tolerance spacecraft. So very, very large, maybe the size of a school bus or something like that. Recently, we've seen kind of a surge of small satellites coming into being launched into space and becoming of interest. It's really taken quite an upswing. So small satellites have proven to be very capable, and they're actually being implemented in space. These kinds of systems are being sent up into space now to do meaningful missions. The miniaturization of parts, higher power systems, things like and so forth. And I know you've probably been reading about the mega constellations, like some companies wanting to send up thousands of small systems into space, of small satellites capable. And it turns out then that these small satellites and these mega constellations are actually economically viable commercially. So there is this interest in then putting them up there. And also, maybe you've seen that small spacecraft are also being implemented to go to be sent off for space exploration. The Marco mission that was just sent to Mars was a 6U CubeSat, which is basically 2 of these side by side. That's a 6U, six of these elements. So think about that. That's going to Mars and being capable. So the aerospace community, because of all this, because things are becoming more capable, has a very, very high interest in small spacecraft. And they have a real prospect of expanding what we currently can do up in space as far as missions. We can expand capability in space, both commercially and for the government. So let me just point out some of the advantages then of small satellites and constellations. Well, as I said, new mission architectures and capabilities. This satellite here is a fraction of the cost of the big satellites that I was talking about before, and the fraction of the risk of the traditional large satellite. If the large satellite fails, you've lost a very, very large capability. But if one of these fails, it's not as big a deal if you've got a number of these working together. This small size opens up launch opportunities, okay? And so launch cost is all about mass. And with these small systems, you can put these on as secondaries on launch vehicles. That becomes attractive then for sending up these small missions. So the small satellites kind of related to this then reduces cost. This is a much simpler system, more risk tolerant, shorter lifetimes. Yeah, you're not going to send this up for 15, 20 years, but rather you may send it up for a few months, and that's okay. Then you'll replace it with other things. The lower mass means, again, lower launch costs, shorter production cycles with higher production rates to stabilize vendors. If you're sending up multiple copies of these, then you have more sort of now like an assembly line going on, whereas the big satellites were traditionally one-off. You would build one of those satellites, but if you have multiple of these, you're building multiple ones, you're getting more confident in the design. Vendors are happy because they are making multiple copies of something, and that's all a positive thing, and it can result in standardization. You can manage risk. These small satellites can serve as test beds in the university environment, like we did with this guy right here, AggieSat-2. We sent up a system for the Johnson Space Center to test out the capability of the new GPS system for them. That's something universities can do, but they can serve as test beds for parts and other capabilities. Again, with being multiple copies, as you're making more and more of these, you're becoming more and more confident in that you've got all the bugs out of the system, so to speak. So that's all positive. Enhancing information. This is really, really neat as far as CubeSats are concerned. These small systems, I should say small sats. If you have multiple of these, you can put these around the orbit. And so instead of taking measurements at one place, you can have a spatial collection of data. So you can get a spatial map, maybe of the space environment or whatever, as well as temporal. So you'll have these things, collecting things not only in space but in time, covering a much wider range of information. Replace. There's this idea, again, I said if one of these fails, a really neat thing is it fails, you have more rapid replacement of a system, whether it naturally failed for some reason or if it was inadvertent or some intentional action. You can produce these faster and you can launch these probably faster as secondary payloads and go up and reinsert back into the system. Reconfigure. Resiliency. There's this worry that if something goes wrong, do you have resiliency? Can you recover from a failure? Well, again, if you have a bunch of these, perhaps you could reconfigure them. You can move some around to make up for the one that failed. And also with reconfigure, once you're finished with a mission, maybe you could reconfigure them and do a new mission after that. And this is really pretty neat. This last bullet is really important. the big satellites that we send up, you're locked in with the technology of when they were built. So the technology gets old very fast, as we know technology does. If you're flying things for a shorter period of time, you have better capability of putting up the latest and greatest sensors and what other systems you have into orbits. You can put capability up more easily than the larger systems that are up there maybe for 15 or 20 years and get dated. Or maybe you want to do something else. So this is really, really kind of a neat facet of working with small satellites and why everybody's so excited about them. Okay, so another really, really cool thing about small satellites, there's a sense in this country to try to get government and commercial companies to work together on these missions. And these small satellites actually encourage commercial participation. They're conducive to viable business models, these small systems. And you see many, many startup companies that are coming in. And I have some in the room who are talking about establishing startup companies, okay? So these small systems are very conducive to viable business models. And of course, then this will promote economic growth and leadership in space commerce in the country as well. So there'll be a positive benefit from that. And of course, why small satellites? Well, it gets students like you excited about working in the profession and learning what it takes to work in the profession. So they're outstanding for what we call workforce development. They're really, really good academic participation. As I said, you can be helping bring down risk for systems for people. And just the fact these are small systems, I mean, you want to make them more and more capable. They provide really a clean sheet of paper thinking and innovation that we need to keep looking over the capabilities we're going to need over the horizon. So these small satellites actually encourage that in an academic environment. So they are a really, really good addition to an academic program. So I'm glad SEDS is doing this here, and strongly encourage it. So these small systems also get one thinking about various research and research topics. Now, I just put a list here just to give you an idea of some of the things, some of the aspects that people are looking at relating to small systems. This is neither prioritized nor exhaustive. So I don't have everything up here. It's just kind of a dump that I thought of things that people are looking at related to small satellite systems. A lot of really interesting concepts up here, you know, to include, here's that rapid in situ manufacturing, you know, 3D printing things in space. There's on-orbit servicing that people are talking about. Of course, exploration. And then all the things that you need to actually make these things viable, like data security. If you have bunches up there, you're going to have interference with the spectrum and so forth. You're going to have bunches of these things. So you have somebody in here was doing data management. All this data that we're going to get together, you've got to assimilate it and you know, come up with actionable information. So all kinds of really, really neat ideas that one can look at related to these small systems. Okay, so there are challenges and opportunities with this high interest in small satellites. I just wanted to cover that, some of the ideas. So of course, over the years, and I just put this quote here from 2011, the National Security Space Strategy from the Department of Defense and the Office of the Director of National Intelligence, that the space domain is so-called contested, it's congested, and it's competitive, okay? It's congested in that there are lots and lots and lots of these small things. There's from thousands of these things up there. So you could have the prospects of collisions. You could have the prospects of interference, the spectrum, RF interference from having multiple systems. Competitive. We have many different kinds of industries that weren't traditionally in space, and now they're starting to think about being in space. The on-orbit servicing. We're talking about space tourism. We're talking about, of course, sending up these mega constellations of satellites. All different kinds of new businesses that are coming into play. So these trends have only strengthened today, and they will continue to do so. That is, there are going to be more and more and more things that are going to be up there. There are going to be new companies that are going to come in. Amateurs are going to be sending things up. New and diverse elements, as I said, space transportation, people doing debris removal, things like that. You've seen like the nets and the things, and all different kinds of ideas. So this has all got to be managed up there. It's kind of a whole new ballgame with these small systems. So related to this then, we talk about space traffic management, space situational awareness, and then the analytics. And that's taking all of this data now that we now have and creating actionable things out of it. So space traffic management involves making sure that things don't collide, okay? Making sure that you don't have RF interference and so forth, things like that. Space situational awareness is being aware of what's up there and also being aware of the environment in which these different elements actually exist up in space. And as I said, it's been recognized that commercial and government partnerships are critical as we move forward, especially in space, given these small satellites that have become pretty much every day. The commercial companies bring the advantage of they are innovative. They have to be. That's part of the business model. They can bring additional data beyond what the government might be providing from space. Typically, a company can do things faster, at lower cost, think about analytics and so forth. So they're a little bit more agile probably than government. So they bring those kinds of advantages to the table. There's really an opportunity for the two communities, the government and commercial, to look at working together. The commercial capabilities could be integrated in new ways and through new business models from what we've traditionally been doing. And that's been kind of exciting, watching the two entities try to figure out how to work together. Now, the government and the commercial companies have very, very different roles. The government its mission is for national security and public safety and good, and commercial companies have to satisfy customers and their shareholders. So we have two different philosophies that drive these two entities, but they can work together and coexist. And the idea is for the commercial companies to complement capability up there, not replace it, but to work together to actually build on what we're learning up there. And of course, it takes communication and transparency from both sides, building a trust to actually get these relationships to work. There have been several very positive effects or positive policies that have come out within the last year. I just put a couple of these here. In particular, the Department of Commerce now has an Office of Space Commerce to help encourage these partnerships with commercial companies. So that's pretty exciting. So there are opportunities now with all these different players in space to establish codes of conduct. We're all going to be up there now. And you see in various of the various areas that maybe we want to have lessons learned or guidelines or things like that. Just start talking about that with the many diverse players, including many international players. So we have to learn how to work together internationally. And again, communication and transparency. So that's the opportunity with the small sats. So I'm going to close just by saying, just pointing out some of the things I'm doing right now, where we're going in the future. Well, we continue to work on this 3D printed model, and it's called SAMS. And so hopefully that will be printed on the International Space Station pretty soon, and then will be sent back down to us to inspect. And then we jumped back in on the University Nanosat program. It's up to Nanosat 10 now. It's at 20 years. So we are AggieSat 6. I said, think about that. So 2, 4, 6. Just happened that way. We didn't go even. It just happened that way. So AggieSat 6 is our latest spacecraft. The idea is we're going to fly 2 6Us. So again, this is a 3U. So 2 of these side by side, it makes a 6U. And the students decided that they're going to work on technologies for this space situational awareness and space traffic management. They're very excited about that. So here they are presenting to the Air Force just about 2 weekends ago, where we kicked off the meeting in Albuquerque. So this is my student leadership team. Everybody's an undergraduate. And so we're going to be looking at technologies like a satellite locator. These 2 6Us, we have an idea for locating another satellite. They want to try differential drag maneuvers to do formation flying. So they fly together and work together. take science measurements in the atmosphere, up in space. And then the Aerospace Corporation has this neat little transponder. You know, like aircraft and ships carry a transponder, so you know where they are. So we're going to work with the Aerospace Corporation to demonstrate this capability with our satellite. And of course, we still focus on adding value to the students' education and building their skill set as they're in the educational program. The other thing that was mentioned, I also had the good fortune to meet up with Mr. Adil Jaffrey, and I know he's a good friend to Rice University. So he's the CEO, but I'm a co-founder with him of Chanda Space Technologies. And what we want to do there is provide we have a commercial opportunity to provide on-orbit inspection, collect space situational awareness data, and also space weather data. That is kind of characterize what's going on in the environment. So we have a NOAA license for a private commercial space-based remote sensing system of satellites that we'll put up there. Again, a constellation of small sats, not CubeSats, but small sats, to collect such information. So I'm going to leave you with a couple of takeaway messages then. So the aerospace community has a very, very high interest in small spacecraft. So this is why there is this huge interest in CubeSats and in small sats. I hope I've demonstrated to you that they can bring some advantages, a lot of advantages, as they complement bigger missions. Small satellites and constellations have become more capable. Something like this can actually provide something meaningful. And they are becoming economically viable. So you're seeing small companies spring up all over the place related to small satellites. So that's very, very exciting that the commercial sector is really kicking in. If you're having multiple satellites up there and they can cooperate, you're suggesting new mission architectures and capabilities at a fraction of the cost and risk of the traditional large satellites. And I hope I communicated that to you. And as I said, new commercial opportunities continue to emerge. And I hope some of you, I know some of you are interested in this, and I hope to see your companies spring up. We're seeing a lot more commercial and government partnerships to try to work this idea of space traffic management for the safety and space situational awareness. These partnerships are forming. It's a very, very exciting time in space, in policy. And so very, very interesting times. And academic participation in small satellites is important. In fact, I think it's critical. We've got to have these small satellite programs in the universities. They provide the basic research and clean sheet of paper thinking and innovation we're going to need for the capabilities over the horizon, as well in workforce development, encouraging young people to go into this profession, go into space. And my experience has been, every young person I've worked with has been exceedingly talented, and I've just been delighted with every one of the young people I've worked with. I want to point out this young man right here. He walked in after we started. That's John Graves. I told some of them they should talk to you because they're interested in the mission controller. Okay, so you'll have some people talking to you. So there he is at the launch of this guy. Okay. All right. So with that, I just want to have some acknowledgments. I am really grateful to every one of the students and colleagues that have worked with us with Aggie Sat Lab and ASU Sat Lab when we were not only Texas A&M but back at Arizona State and all the other colleges and universities. Every colleague and student that have participated in these programs. I want to thank the Rice Space Institute and is it Weiss School of Natural Sciences? Is it Weiss? Weiss. And the Weiss School of Natural Sciences for this invitation to speak. This is very special for me to be able to do this, and I really, really appreciate that. And of course, all of the companies and NASA centers and Air Force and all who've helped these students actually build satellites and actually launch them and see that they can actually participate in such things. Then various other people down here. Joe Perez, he works at ATA in Albuquerque, but he was very, very key in my lab in helping set up the processes that we do, the industry practices and things. So always a call out to him, and then everybody else who's participated in some way, shape, or form in the satellite programs in which I've had the privilege to be involved. So with that, I will take any questions.
So I had a question about the SAMS project that you have. Yeah, the SAMS project.
Yes.
What percentage of the satellite, is it just the structure you're printing, or are you actually printing some functional components?
At this point, we're printing just the structure, but the students are designing the rest of it now, boards and things like that. We'll have to send up some things. I don't have a percentage at this point, but we want to minimize how much we have to actually put in. But
So
for
you're
now,
gonna,
it's
are you
structure.
gonna launch some parts to
That
install?
we'll have to. We'll have to send some parts up. But that would be the idea. It would be to send some parts up on a shelf, and then as something is needed, they would be able to print something and then toss it off into space.
Yeah, so are you gonna print one and launch one, or are you just gonna print it and bring it back?
This one we're going to print up there and have it brought back down to the ground, so we can look at it and see how it went
Yeah.
in the space environment. We have a 3D printer in the lab, so we've been practicing. We have these things all over the lab, as you can imagine. But the idea is to print one first and get some experience with that, and then the students are working on a modular one where they can just slip in boards and things like this, make it very modular, and see slots for boards and things, with the idea that then they could just tell it they want a certain capability, put it together, and then send it off. Did that answer your question?
Yeah, yeah,
But as
the
more-
IKEA model.
The IKEA model, there you go. But as 3D printing gets more and more capable as far as the metals and the electronics and things like that, of course, eventually it'd be nice if you could do the whole thing.
Yeah. I was just wondering how far into function you were going.
As far as we can with what's able to be done. Yeah.
So while people are getting over their nerves about asking a question, let me ask one. So, like the last, you're talking about the space situational awareness. So, in all these programs, how much freedom do you give the students to come up with what they want their satellite to do, or is that governed by perhaps what your customer, for Air Force or whoever would like to see, or how much? I mean, that's quite a challenging set of things in the last satellite they've picked. Did that all come from the students because they thought this was really a challenging project that they wanted to try and do, or is it because that's what the Air Force is looking for right now or something? How much do the students get involved in?
Just as the SEDS team is doing, coming up with their experiment that they want to do, the students came up with those that they wanted to do.
Okay.
They researched them. They thought that would be neat. They read up on what was kind of needed, what were the challenges, and they came up with some of these ideas. So I try as much as possible that the students come up with what they want to do. I want them to own it.
Right.
And if they own it, then they'll shepherd it through to the end successfully. Right. They better chance.
No, I think that's important. And in case for some of you who don't know, Helen's mentioned SEDS a couple of times. So we have a chapter of the Students for Exploration and Development of Space here at Rice, and so they're one of the things that they're doing. I think some of the students at Ryan here runs it, and there's a few other students in here from there. And so they're looking to participate in their first ever CubeSat competition. So that's another good reason for having Helen on campus here. Ryan's not shy, which is a good thing.
Don't rip this.
No, that's fine. So hey, I'm Ryan Udell. I'm the president of Students for the Exploration and Development of Space here at Rice. So one of the things we're doing is developing a 1U CubeSat as part of the national competition. We're currently competing against 6 other teams, including SEDS, Texas A&M. And right now we're thinking about either doing something with mapping vegetation growth or tracking high energy particles moving across the universe.
So as far as I understand, some of those instruments may be instruments that would be relevant to other research projects at Rice, but you guys are picking out what you want to send up. So that's kind of the... Right,
and I think that's very important. I'm wanting some questions here, so guys. I'm surprised no one has asked about space debris yet, but now I've planted a seed. I was just in a conference in Scotland last week where the sole purpose of the conference was to look at how data from space can be used for anything. Fish farming, mining, monitoring mining, looking at illegal. fishing, all sorts of things. And a lot of those companies that are being developed around this concept are either using or building and flying their own CubeSat. 1U, 2U, 3U, 6U, maybe even 12U. But it's such a big area now that getting our students, and I think we've got a lot to learn from what's happening at A&M, as much as I hate to say that at Rice. But no, A&M is one of the lead centres for this kind of thing, and I think all the things you said, I think is fantastic. It takes the students through that process.
Right.
And I think
and they're on the cutting edge of what's being, where the industry is going.
Right. And I sometimes talk about this is like the cell phone revolution in space, where you buy a new cell phone. Well, maybe some of us older people don't, but you buy a new cell phone every iteration, every year. This is what's happening with CubeSats. You mentioned you change the technology and you fly the latest, and it's cheap enough to do that. I'm still bumping my gums. I'm looking for a hand up for thank you.
I don't need that.
No, you do. We're recording it.
We're recording it, so sorry.
Well, I'm wondering if any of this stuff is recyclable, if you can somehow retrieve it after it's done its 3 or 4 months worth of value, and then melt it down and start over with it.
Well, typically it'll burn up in the atmosphere coming back in. So, I mean, there are some things. Of course, you want think capsules with the astronauts, and you want them to come back, obviously, and things like that. But most satellites are burning up. You want them to burn up. But I know people are talking about having reusable systems that'll come back down, so the balut and things like that. So I don't know that there's a lot of recycling of what's up there. I think it just burns up. Now people are talking about, okay, to the elephant in the room, you want to bring up the debris.
No, well, I mean there are companies like Chanda is a little bit different, but there are companies like Chanda who are looking to do the space debris cleanup.
Yes.
Now, they haven't talked about what they do with the stuff that they collect. They may actually just gather it up into a giant ball and have it burn up.
Yeah,
but that's an interesting idea, is how they might be able to reuse some of this stuff. But you're looking shocked, but it's...
It burns up.
These are tiny little things, and the atmosphere is kind of big. I know what you're thinking. I can see it. But you're right.
She's very distressed.
But I think that right now that's the solution that we have. I mean, you can leave them up there, and there's stuff up there that's been up a long time. But they provide dangers for things like the space station or for future satellites. So we have to burn it up in the atmosphere, I'm afraid.
Thanks for your time. I got 2 questions. So my first question is, if you think the government is adequately managing the risk associated with having so many small satellites, given, the catastrophic, consequences of having these, where it can snowball and you have all this debris blocking, then the orbits of potential future satellites. And then the second question is, as this opens up to international, other nations have more access to space, and we get even more and more of this. How do you manage that space adequately?
No, those are great questions. No, I think the government is making good progress in this area. Some of these policy directives that have come out. I think everybody's starting to work together to manage these 2 areas: traffic, space traffic management, and SSA. So I think we're making progress in that. Now the international, that's tough. And you said you were at an international conference. So there are international organizations that get together, like to talk about debris, and there are international guidelines, like you can't put something up there that's going to stay up there for longer than 25 years. You have to dispose of it within 25 years. But there are international groups that are getting together to discuss these things. I don't really have an answer, but I know that people are talking.
But it is an interesting challenge. I mean, I think in the US, for sure, you have to, if you're launching anything, even a short-term CubeSat, there's a deorbit plan, just so that, it could be 25 years, I think is the current the current number. I think Europe probably buys into that too, and there are international
Oh, yeah.
regulations.
No, nobody wants collisions, because
Right. The
collisions
question-
ruins it for everybody.
Yeah,
That's-
I mean, the
that's
question
just a
is when
fact.
there's a lot of activity going on now with what we call a little bit snobbishly emerging nations. India's launching a lot of things. They launched, I think, 108 CubeSat. Was it 108? I can never get it. Somewhere 100 and something satellites at once in one launch of this size. China's launching a lot of stuff, and so most people are buying in, but you never know. And there's a lot of launches in every country that we don't hear about, unless you see the rocket plume. So, but I think overall people are really working together to make sure that this is not a problem for. We've had a couple of major accidents that produce major clouds of space debris, and that's affects everything from the space station to other rocket launch, other satellite deployments.
And actually, there's also effort to look at some of the maybe larger bodies that are up there, maybe spent rocket, rocket bodies and things like that. That they perhaps are going to provide maybe a more catastrophic collision probability than the satellite. So it's not just the satellites, but it's the other things to launch the satellites up there that we have to be thinking about cleaning up as well. So.
Yeah, I think by mass the biggest effect is Russian second stages, and by number it's a couple of those collisions, the Chinese anti-satellite test.
ASAT,
and
yeah.
Yeah.
But fortunately, if it gets ruined, it's ruined for everybody, and everybody realizes that. So I think there's this willingness, at least from most, to want to talk about it and see how to mitigate it.
So following on from that, you'd mentioned obviously if you're going to launch your satellite, your students are going to launch a satellite, they have to follow all the regulatory rules, right?
Yes.
So
yes.
Do the students do that themselves too? Do they read up and make sure that they fill in all the paperwork, and then somebody in the legal office at A&M checks it, or how does that work? Because it's a very important aspect.
Well, it'll depend on the program. The program that we did with the Johnson Space Center, JSC helped us with a lot of the paperwork. But again, on some of the missions, I've had the students actually communicate with the FCC to get licensing with NOAA and things like that. So it's good experience that the students actually work with the federal agency as well. And we found the federal agencies, at least our experience has been that they've been very willing to work with the students.
So I have one more question for you.
Yeah.
Could you sort of give me a characterization of the push-pull? So how much of your time do you spend tugging people in versus people just showing up on your door saying, hey, I've got this need, I need you to go do something for me? So what's your experience so far, and has it changed over time? Does that make sense?
Are you talking about students coming in?
No.
What are
I'm
you
talking about sponsors, people that
Sponsors.
Want to send stuff up, and
haven't really had a lot of
you say
that.
you had like 55 companies, right?
Well, that's they're relationships that we have fostered. We've gone out and made those relationships.
So they're almost all sort of where you.
Correct.
You talked it up.
The students and I have been the initiators. Yeah.
And said, hey, we have this great new thing that's going
to say, hey, we'll give you this check to do this. But you have to do a lot of legwork. You and the team has to do a lot of legwork. Yeah, it's a lot. It's a lot of work, but it's really worthwhile. It is so worthwhile to do. Did that answer your question?
Well, I was just wondering if suddenly people hear about you and somebody just shows up. Does that happen?
Well, they come and they want to hire the students, and that's fantastic. So that's putting a stamp on them that the program is doing good things for the students. But as far as coming in with parts and things like that, not really. It's mostly initiated on our end to establish the relationships, which is good. The students learn how to go and build those bridges. No, it's fantastic. It's a lot, like I said, it's a lot of work, but it is so worthwhile. I've found it to be very worthwhile. Would I do it again? Absolutely.
So what's the payback for getting into the trash business? For going and knocking stuff out of orbit and cleaning it up?
Well, the payback would be that means you're less likely to run into stuff. What are you talking about?
I'm talking about this. So is there any financial incentive? I mean, if you want to go,
Well, I'm not in the trash business, so I don't. I'm
I'm talking about the space trash.
I understand. I'm not in the I'm not in the orbital debris business. So I'm not sure. I'm not sure what their business models are, but
right.
you know, they may be being financed by governments to clean up. I'm not sure. It could be you know, if they build it, then somebody will contract their services to, you know, maybe clean up a certain orbit or something like that, I would imagine.
But I can't imagine doing that very effectively unless you had some kind of a propelled vehicle to come
I
and
understand. I totally
capture
understand. It's a very complicated problem, and everything's in different orbits. It's 3D. It's spherical, so it's all, you know. It's a challenge to move around in orbit too. So
No, I
totally
understand.
understand. No, I mean as far as from the business model standpoint, you know, propellant to get from one, you know, one inclination to another, it's costly, and so I have not dug into the business models, but I would presume if they put the capability up there or offered it, they think somebody's going to come and want them to maybe clean up a certain popular orbit or something, or maybe there's a, you know, some piece of debris that's getting in everybody's way. Everybody's having to maneuver too much, so maybe somebody contracts for them to get rid of it.
yeah, build a
haven't
drone
dug into their
or
business models.
whatever and go
No, I
after
understand.
it.
I understand, yeah. But I don't see.
I thought Sandra Bullock just needed
I
a
don't
fire
see them,
extinguisher
I don't see them
to.
bringing it like all back down and recycling it. No, I get that. I'm just saying. I get
Yes.
it. I know.
Yeah, I was saying, I think Sandra Bullock just used a fire extinguisher and she could go anywhere she liked, right? But I think there's another big challenge, and it's because it's who's going to pay for it, because who's going to take responsibility for, you know, a lot of this. Well, for instance, if the Chinese blew up a satellite and that's the big cloud, are they going to pay for somebody to clean it up for someone else? There's all of these other issues
That's
that
all
come
these
into
international
Exactly.
conversations that go on, yeah.
So it is a good question, is
No,
what
it's a
really
great
is the
question.
business case as to how you might
Right.
make money by doing
Incentivize
this.
somebody to put these systems together.
It needs done. The question is who's going to pay to have it done.
Right,
I mean,
right.
that's,
I mean, you don't want to build something and not get paid for it.
it's
I
a
get
big
that.
challenge,
Yeah, you bet.
Colin.
Just want to ask what you find as the biggest challenge for any of the student-run CubeSat programs.
I would say their time, students' time. They get pulled in all different directions. It's time.
We'll find out how good
And
the
continuity, you know, they graduate, you want to be sure everything's captured. Continuity and time management, I would say. Would you say, John, time management?
Time and something that's very hard to learn, especially early on, is how important it is to document what you're doing.
Yeah.
Further
Yep.
appropriate knowledge capture, and
Yep.
have something to pass on.
Yep. So that's a challenge, is making a documentation system that does the job, but it's friendly enough that the students will embrace it as a tool that they will use. That's evolved over the years, the system that we have. So they do paperwork.
Okay, I think one last question at the back here.
Yeah, first I'd like to thank you for coming here to Rice, and also David for putting this together. Have you noticed that Planet company in San Francisco has produced just gobs of satellites that they're putting out, and they're having more businesses they can shake a stick at as far as the getting the photos real time almost. About every hour and a half they can get a whole grasp of the whole planet, just like you would get on your Google
The
Maps.
temporal and spatial coverage like we were talking about,
Yes,
absolutely, yeah.
right. With that happening, are you guys, both Rice and A&M, able to tap these companies like Planet and get them to come down and talk to the students maybe, or get them involved in that way, connect them with the companies in that way?
Yeah, the companies, we have found that companies are willing to be, you know, mentors for the students, or and help in that way, because they're ultimately looking for hires. They want to hire hire the students into their companies. So we have found the companies we've talked to that we've approached to be receptive to helping with questions and things. I mean, we can't dig into the proprietary nature of things that they do, and it may involve an NDA, a non-disclosure agreement, or something like that. But we've actually found people to be receptive to working with the students. It's been very positive. Does that answer your question?
That does.
Okay.
Thank you.
Yeah, they're doing some really cool stuff, aren't they? Planet, oh my gosh.
Well, thank you very much. I mean, I think, as you've probably seen, this is a really a big growing area, and being able to, I mean, we just had our board meeting for our professional masters today, and telling us how we need to train our students to be able to do systems management, which we don't, I mean, you can only get so much of that from classwork. And seeing the kind of things that Helen's doing at A&M, where the students are working their way through every step of the process, is really invaluable. I mean, and it's something, I think with the SEDS project here, I'm hoping that we can do more of it, Rice, and hopefully we'll be able to call you up and ask your advice, or, you know, students and former students. So personally, I'd like to thank you again.
Let me just make one more comment about the systems engineering thing. I want to, hats off to the University NanoSat program. Talk about a program that has evolved over the 20 years. They now are going to have weekly telecons with the student team to go over the whole design process, and they've got a whole user's guide set up. They've got people at the Air Force, to the kids to be on call. Part to your question, to help the students learn how to do this. And they say, this. And I agree, I've always agreed with this, but to do systems engineering and program management and all these things, you really have to do it. You can't, you can see it in a class, which is valuable. You've got the ideas, but to actually put it into practice is really where it starts to sink in. And you start to see what works for you and maybe ways to do things. So hats off to the Air Force, but they're actually providing that for the student team. Again, partly to your question, we found the community to be very, very receptive in helping the kids. And the Air Force has been phenomenal, absolutely phenomenal.
Great. Well, please join me in thanking our speaker. Thank you. And keep your eyes posted. Again, we think it's going to be March 6th, but we'll send out the information. Parker Solar Probe, how you make a satellite survive in a million degree corona. But hopefully we'll see you again, and good luck with the weather going home. Thank you.